All right, so acids are sour. What makes some?
Like, let's say like a lemon or a lime.
Yeah, lemons, lime, citric acid. The citrus fruits are acidic because they make citric acid. The properties of acid come from free H pluses. Now think about an atom of hydrogen. What's in an atom of hydrogen? What are your subatomic particles for an atom of hydrogen? The nucleus is just one proton, and there's one electron whirling around it. To get H plus from H, we remove the electron, leaving you just a free proton. So H pluses are just free protons. And you have channels, proton channels in your body, in your tongue, that let it go through your tongue, and that then tastes as sour to you. But there's other parts of your body that are also tasting for this. So like in your heart, you have tasters, and they're tasting for blood acidity. And so this is an easy thing to test for because there are specific channels that H pluses will go through. So lemons and limes are acidic because they have citric acid in them. The first theory of acids and bases came from Arrhenius. Whoops, that's not showing up. And he said an acid is a solution that contains an excess of H plus ions in aqueous solution. So in his theory, acids were compounds that contain H plus, and when they dissolved in water, they would release a free H plus. Acids have a sour taste. They'll turn litmus paper red, and they react with metals to produce hydrogen gas. They react with bases to produce a salt and water, and they react with carbonates to produce carbon dioxide. So if you put vinegar on baking soda, it erupts into gas because the carbonate, sodium bicarbonate, is reacting with the acid to form carbon dioxide, which is the gas that is being elicited. Arrhenius bases. A basic solution that has an excess of hydroxide ion. Bases are bitter to the taste. They turn litmus paper blue, and they have slippery, soapy textures. Now, this is actually one of the reasons why bases can actually be more dangerous than acids. Is that if you get an acid on your body, you can tell right away. It's prickly, it's stinging, because you have a lot of receptors for acids. If a base gets on your skin, you won't notice it right away. Touch it, it'll feel like slippery soaps on you. But because you don't feel it right away, it has a lot more time to do damage. And so in the end, it can cause a lot more damage just because the person's not aware of it until it actually really starts damaging the skin. Whereas with an acid, as soon as it makes contact with you, because you have so many receptors for this in your body, you know about it immediately, and you can pretty much wash it off immediately and not have any problems. So, the next set of acid-base theories came from Bronsted and Lowry. And Bronsted and Lowry said that an acid was a proton donor. It would release an H plus to something. And a base was a proton acceptor. And that was important because that brought ammonia and all the alkaloids into the field. Where the Arrhenius bases, like magnesium hydroxide, sodium hydroxide, potassium hydroxide, they're a hydroxide containing substance, which when you dissolve them in water, release this OH minus. The Bronsted-Lowry base brings in all the nitrogen compounds, which don't have any hydroxides. There is no hydroxide in ammonia, it's just NH3, but it'll accept an H plus from water, leaving an OH minus. And so this new level of theory brought in all the nitrogen compounds. When an acid gives up its proton, what's left is called the conjugate base. And when the base accepts a proton, what's left is called the conjugate acid. And in general, reactivity goes from strong acids and bases to weak acids and bases. So hydrochloric acid is a lot stronger than H3O+. Water is a stronger base than Cl-. It always moves in strong to weak direction. Here, bicarbonate is a base, so once it accepts a proton, it becomes a conjugate acid. Water here is acting like an acid. Once it donates a proton, it becomes the conjugate base. Notice that water can be an acid or a base, and we're going to call that amphoterism. Some compounds are amphoteric. They can be either an acid or a base, depending on what their chemical environment around them is. They can do either. It all depends on what's happening around them. Identify the base in the following reaction in the compound's conjugate acid. Well, they want the base. So who is accepting a proton? Water. Water accepts a proton. So water is your base. And then the conjugate acid is H3O+, because once the base accepts a proton, now that's an acid. It can donate that proton. Then the final theory, Lewis acids and bases. This deals with electrons. A Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. And this is useful especially in organic chemistry, because your solvent won't be water anymore, so you really won't have H pluses and OH minuses all the time. And with this theory, this actually brings most organic chemistry into the theory of acids and bases, because you have electrons attacking stuff. And so this is the most comprehensive, most technical definition. We don't do much in this class with it, but in future chemistry, most acid base is Lewis acid, Lewis base. So like for example, this reaction, boron trifluoride is the Lewis acid because it accepts 2 electrons. Ammonia is the base because it donates 2 electrons, giving you this complex. And this doesn't qualify for Arrhenius acid-base theory. There are no H pluses, there are no OH minuses. This doesn't count for Bronsted-Lowry acid-base theory. No one donated a proton, no one accepted a proton. But it does qualify for Lewis acid and base. And so this is a much more comprehensive theory that will encompass an umbrella a lot more reactions. All right. So here we have Arrhenius' theory, Bronsted-Lowry's theory, and the Lewis acid-base theory. Reactions of acids. They react with metals to form hydrogen gas. If, and only if, that metal is more active than hydrogen. We remember the activity series. There were a couple metals that were less active than hydrogen. Copper, silver, gold, and mercury were all less active than hydrogen and will not react in a simple acid like hydrochloric acid. But if the metal does react, it will dissolve and displace hydrogen and kick out hydrogen. Acids will react with bases. This is a neutralization reaction. And in a neutralization reaction, when water is your solvent, you end up with a salt and water. So whenever a strong base and a strong acid meet, the H plus and the OH minus combine to form water, and the other cation and anion combine to form a salt. So a salt and water are always your neutralization products. Any questions on that? Questions at all? It's pretty much how deionizers work. If you see the word deionized water, the water gets run through a chamber and it has a lot of H pluses that are bound to these little beads. And your ions, your magnesiums, your irons, your sodiums, everything gets switched out for an H plus. So you go through one canister and all your cations were replaced with H pluses. Then you go through a different canister and all your anions are replaced with OH minuses. All your chlorides, bromides, iodides are switched out for OH minus. And the H pluses and the OH minuses come together as water. And so what you end up with after both canisters is super pure water. It's like 100% pure water. So again, for neutralization reactions, acid plus base forms a salt and water. Reactivity with metal oxides is the same as with metal hydroxides. You get a salt and water, which is why we consider metal oxides bases, just like metal hydroxides. So the word salt is not a super technical term, but a salt is any ionic compound that's not a base. And so the family of ionic compounds are anything that's held together by an ionic bond, a positive and negative charge holding themselves together. And there's 2 types of ionic compounds, bases and salts. Bases are the group 1 and 2 metal oxides and hydroxides. All the other ones are salts that are formed from neutralizing acids and bases. Reactivity with metal carbonates. As we said, when an acid reacts with a carbonate, you first form carbonic acid, but that is inherently unstable. And so the carbonic acid rapidly breaks down into water and carbon dioxide. Which is why carbon dioxide is an acid anhydride. Because carbon dioxide can react with a molecule of water and form carbonic acid. And so when you get distilled water, it's always slightly acidic. Just because there's carbon dioxide in the atmosphere, and that carbon dioxide will dissolve into your water you've distilled, and it reacts with the water to form carbonic acid. So when you distill water, you actually expect the pH to be a little acidic, like 6, 6.5, something like that, to take into account the carbon dioxide that dissolves in from the atmosphere. Any questions on that?
So, we'll have to know about the different types of reactivities to each different thing, and like what they, is that pretty much what we got to know with
Yep.
those? Okay.
Sure. And I'll send you guys a study guide today. Then
So as
we'll
you start filling it out.
work through it on Wednesday, and Monday is another day for questions, and test on Tuesday.
Okay.
All right, bases can be amphoteric, like we said. Water, we earlier saw water act as both an acid and a base. Here, zinc hydroxide can act as a base when it reacts with hydrobromic acid to neutralize it into a salt and water, or it can act as an acid to form this complex compound. Sodium hydroxide and potassium hydroxide can also react with metals like aluminum to form this compound. And that's pretty much how Drano works, the powdered stuff. It's these solid bases with little aluminum chips. And this reaction produces a lot of heat. And the purpose of that is if you have like a congealed hairball or something in your pipes, it will melt through and then things will start flowing again. And so a lot of the liquid plumbers are based off of basic solutions. Because you can't throw acid down pipes. Pipes used to be metal. These days they're mostly PVC, but still there are some metal components in the sink. And so an acid will eat through that, whereas a base won't. And so bases are used for that type of stuff. Salts. These are products from acid-base neutralization. Strong acid and strong base forms salt and water. Salts are ionic compounds. Ionic compounds are anything that's held together with positive and negative charges. However, we don't count the metal oxides or hydroxides. Those are bases, not salts. Salts are generally crystalline compounds with high melting points and high boiling points. There are some exceptions. Salts that are liquid at room temperature are called ionic liquids. And it's definitely an academic curiosity. It's used industrially somewhat. Because the salt has no vapor pressure. Because a salt is positive and negative charges, which hold each other really tightly. And so if you have a liquid salt, that's a solvent that won't escape, and that has a lot of uses industrially. Which salt forms in the reaction of aluminum oxide and hydrobromic acid?